Find somewhere comfortable tonight, wherever you are, bed, chair, somewhere quiet in the dark. Let your body settle into whatever is holding it. You don't need to concentrate on any of this. You don't need to remember a single word. If you drift partway through a sentence and surface somewhere else entirely, that is exactly what this is for. Tonight, we are going to talk about cities, about the strange, slow, invisible thing that happens when human beings pile stone upon stone, lay road after road, and build upward until the sky is a narrow strip between towers. We are going to talk about warmth, where it comes from, where it goes, and why. On a summer night in a city, it sometimes seems like the air itself has forgotten how to cool. It is a gentle story, really. A story about a man with a thermometer walking between fields and streets 200 years ago, about sunlight and stone and the way heat hides inside concrete long after the sun has gone, about trees and what their absence costs, about the air above a city at 3 in the morning, still faintly warm, still slowly releasing the memory of the day. You don't need to follow it closely. The words will arrive and they will pass. Some will stay. Most will dissolve into the quiet. And somewhere in the middle of all of it, if you are lucky, sleep will find you. We are in no hurry tonight. The story will carry itself. All you have to do is rest. There is something worth noticing before we begin in earnest about the nature of discovery. Most of the great scientific revelations we tend to celebrate arrived with fanfare. A comet spotted, a continent mapped, an equation that changed everything overnight. But some discoveries are quieter than that. Some of them arrive simply because one person decided to pay attention to something everyone else had already accepted without thinking. The warmth of a city is like that. It was always there. People had always felt it. The way the air in a busy street felt close and heavy compared to the open fields beyond the city's edge. The way a winter evening in the center of town was somehow less biting than the same evening in the countryside a few miles out. But feeling something and formally noticing it are different things. For a very long time, no one had thought to write it down. Until one man did. And what he found, walking between fields and streets in the early years of the 19th century, was the beginning of something we now call urban climatology. The science of how cities make their own weather. The story starts in London, and it starts with a thermometer and a quiet, careful mind and a willingness to simply keep walking and keep measuring until the numbers told their story. The man who first felt the city's warmth. Luke Howard was not a professional scientist. That distinction matters, and it is part of what makes his story so quietly remarkable. He was a pharmacist by trade, a Quaker by faith, and a meteorologist by the most sincere kind of compulsion, the kind that makes a person wake before dawn to read a thermometer and sit by a window watching clouds when there are better things to do. He is probably best remembered, if he is remembered at all, for something he did in 1802. He gave clouds their names: cumulus, stratus, cirrus, nimbus. These words that we now use without thinking, that appear in every weather forecast and every child's nature notebook, were Howard's invention. He presented them to a small scientific society in London on a winter evening, and the names spread across Europe within years, translated into French and German and adopted by meteorologists everywhere. But the work that concerns us tonight came later, and it was slower and more painstaking, and it has perhaps never received quite the attention it deserves. Between 1818 and 1833, Howard published 3 volumes under the title The Climate of London. They were dense with observation, years and years of temperature readings, rainfall measurements, records of fog and frost and wind, all gathered with meticulous patience. And woven through all of it was something that Howard kept returning to. Something that nagged at him with the quiet persistence of a fact that refuses to be ignored. London was warmer than the countryside around it. Not dramatically warmer, not in a way that would strike a casual observer as extraordinary, but consistently, reliably, measurably warmer, and Howard had the numbers to prove it. Comparing his urban readings with those taken at rural stations outside the city, he found that London's temperature ran, on average, about 1.5 degrees Fahrenheit higher than the surrounding fields and villages. In modern terms, that is roughly 0.8 of a degree Celsius. It does not sound like much. But Howard understood that this was an average across all hours and all seasons, and that the true excess was often considerably larger on calm, clear nights when the contrast between city and country was at its sharpest. The difference could be several degrees. He noticed other things too. He noted that frost came later to the city than to the fields, that snow melted faster on London's streets than on the ground a few miles north. Picture him, if you like, on one of those walks. It would have been quiet by our standards. No cars, no electric light, the streets lit by gas lamps casting soft pools of yellow on the cobblestones. He would have carried a thermometer and perhaps a notebook, and he would have walked from the denser streets of the city centre outward toward the fields of Tottenham and the open ground to the north, reading the temperature as he went. And the numbers would have told him every time the same thing. The air grew cooler as the buildings thinned and the trees thickened and the stone gave way to soil. What he was measuring, though he did not yet have a name for it, was what we now call the urban heat island effect. Howard had his theories about why this might be. He speculated, with remarkable prescience for a man living in 1820, that two things were primarily responsible: the burning of fuel and the density of habitation itself. London, in his time, was already burning enormous quantities of coal, in furnaces, in fireplaces, in the boilers of the early steam engines that were beginning to change the face of manufacturing. And it was densely packed with people and animals and all the metabolic warmth they generated simply by living. Howard thought these sources of direct heat were the main culprits. He was partly right, but the full picture, as we now understand it, is considerably richer and stranger than he could have known. The name itself, Urban Heat Island, came later. It was coined in German as Städtische Wärmeinsel by a meteorologist named Albert Pepler in 1929. The German is rather beautiful, if you let it settle. Städtische meaning urban or civic, Wärmeinsel meaning literally warm island, a pocket of warmth surrounded by cooler air, the way a real island is surrounded by sea. The image is apt. Epokut, a city viewed from above on a clear night with instruments sensitive enough to measure temperature from the air, glows warmly against the cooler dark of the surrounding land. It is an island of heat, and it is one that the city has made for itself. By the time Pepler gave it a name, the world had changed enormously from the London that Howard had walked through. The Industrial Revolution had accelerated beyond anything Howard could have imagined. Cities had grown not just in population, but in physical extent. The stone and brick and asphalt spreading outward across what had been fields, the buildings rising higher, the streets multiplying. The warmth Howard had noticed in London had become a feature of every major city in the industrializing world, and it was growing stronger with every decade. Howard's work was quiet detective work. He was not looking for a revolution. He was simply paying attention, season after season, year after year, to the numbers that his thermometer gave him. And the numbers kept telling him the same thing. The city was different from the land around it. It was its own kind of place, with its own kind of climate, subtly but measurably distinct from the fields and forests beyond its edges. That observation, so simple, so patient, so careful, is the foundation of everything that follows. Stone, tar, and sunlight. Why cities absorb the day. To understand why a city is warmer than its surroundings, you have to start with sunlight. not with buildings or roads or the particular details of urban life, but with the most fundamental thing: what happens when light from the sun arrives at a surface and what that surface decides to do with it. Sunlight is energy. It travels across roughly 150 million kilometers of space as electromagnetic radiation, waves of energy moving at the speed of light, and when it finally arrives at the surface of the Earth, it has a choice to make. Or rather, the surface has a choice to make for it. Some of that energy will be reflected back upward, bouncing off the surface and returning to space more or less as it came, and some of it will be absorbed, taken in by the material, converted into something else entirely, something we experience as warmth. The fraction of incoming sunlight that a surface reflects is called its albedo. The word comes from the Latin for whiteness, which is fitting because pale surfaces tend to reflect more light and dark surfaces tend to absorb it. Fresh snow has an albedo close to 9/10. It reflects almost all the sunlight that falls on it. A dense forest sits somewhere around 1/5 to 1/4. But fresh asphalt, the material that covers so much of a city's ground, has an albedo of around 1/20. It reflects only about 5% of the sunlight that strikes it. The remaining 95% is absorbed. Now think about what that absorption actually means at the level of the material itself. A photon of sunlight, a tiny packet of electromagnetic energy, arrives at the surface of a dark road. It strikes a molecule in the asphalt. That molecule absorbs the photon's energy, and the energy does not disappear. It becomes motion. The molecule begins to vibrate more rapidly, jostling against its neighbors, which jostling against its neighbors. This cascading increase in molecular vibration is exactly what temperature is at its most fundamental level. Temperature is not a thing that exists independently of matter. It is a measure of how fast the atoms and molecules in a substance are moving. When the photon's energy becomes molecular motion, the asphalt gets warmer. And here is where the difference between city and countryside becomes stark and physical. The materials that cities are built from, asphalt, concrete, brick, stone, have a remarkable capacity to store thermal energy. Concrete, in particular, can hold roughly 2,000 times as much heat per unit volume as an equivalent volume of air. Think about what that number means. The air above a street, even on a hot day, contains very little stored heat. It warms quickly, but it also loses that warmth quickly because there is simply not much of it, and it moves around. But the concrete beneath your feet, or the brick wall beside you, or the tar of the road, these materials are dense and solid, and they can absorb and hold vast quantities of thermal energy without their temperature rising dramatically, because the heat is distributed through so much mass. A city is, in this sense, a colossal thermal battery. All day long, from the moment the sun rises, its roads and rooftops and walls are absorbing solar energy and storing it in their bulk. The surface temperature of a dark asphalt road on a sunny summer afternoon can reach 60 or even 70 degrees Celsius, hot enough to cause burns, while the air a meter above it might be only 35. The road is holding an enormous reservoir of heat in its depth, and it releases that heat slowly over many hours. This slow release is the key to understanding why the urban heat island is most pronounced, not at noon, when the sun is highest and the city is absorbing energy fastest, but after sunset, when the sun has gone and the countryside has already begun to cool. In a rural landscape on a clear summer evening, the cooling happens relatively quickly. The ground has less thermal mass than urban materials, and without vegetation trapping warmth, the heat that the soil absorbed during the day radiates upward into the clear sky and dissipates. The temperature drops noticeably within an hour or two of sunset. The air over a field at 10 in the evening can be several degrees cooler than it was at 6. But in a city, the stone and concrete and asphalt are still full of the day's heat. They release it slowly, hour by hour, warming the air above them through the night. The The buildings themselves, their walls thick with stored warmth, radiate heat inward toward the street and outward into the air. The city does not cool quickly. It cannot. It has too much heat stored in too much material, and that material gives it up reluctantly, gradually, across the whole of the night. There is another factor that amplifies all of this, and it has to do with the geometry of the city itself. But we will come to that properly in a later chapter. For now, it is enough to hold the image, sunlight arriving, being absorbed rather than reflected, becoming heat in the deep mass of urban stone, and then slowly, patiently giving that heat back to the air through the long hours of the night. The contrast with a meadow or a field is not just a matter of albedo, of how much light is reflected versus absorbed. It is also a matter of what happens to the heat that is absorbed. A field absorbs solar energy too, but a field has something a road does not: water and life, and the remarkable process by which living things use solar energy to do something other than simply get warm. That process, and the profound difference its absence makes in a city, belongs to the next part of our story. The missing forest, evaporation, and the cooling that never comes. On a warm summer day in a forest, something invisible and extraordinary is happening. The trees are sweating. Not in the way we do, not from exertion or discomfort, but in a very real physical sense. A mature forest on a sunny day is lifting enormous quantities of water from the soil, drawing it up through roots and trunk and branch and leaf, and releasing it into the air as vapor. A single large oak tree can transpire several hundred liters of water on a warm day. A forest of them, stretching across a hillside, releases so much water into the atmosphere that it can influence the humidity and rainfall of an entire region. This process, combined with the simple evaporation of water from soil and puddles and stream surfaces, is called evapotranspiration, and it is one of the most powerful natural cooling mechanisms on Earth. To understand why, you have to think about what it actually takes to turn liquid water into water vapor. Water molecules in a liquid are constantly moving, jostling and bumping against each other, held together by the gentle attraction between molecules. To escape into the gas phase, to become vapor, a molecule at the surface needs enough energy to break free of those attractions and fly upward. That energy has to come from somewhere, and where it comes from is the surroundings. When water evaporates from a surface, it draws energy from whatever it is resting on: the soil, the leaf, the skin. That energy is called latent heat, and the name captures something important about it. It is heat that has gone into hiding. It has not vanished. Energy does not vanish, but it has been converted from the kind of heat you can feel into the kind that is locked inside the water vapor molecule, invisible and unfelt, until the vapor eventually condenses somewhere and releases it again. The consequence of this for air temperature is direct and significant. Every joule of energy that goes into evaporating water is a joule that does not go into warming the air. In a forest or a meadow, a very large fraction of the solar energy absorbed by the surface is consumed in evaporation rather than in raising temperature. The ground stays cooler, the air above it stays cooler. The process is essentially a continuous, passive air conditioning system running silently as long as there is sunlight and water. Now consider what happens in a city. Cities are, by design and necessity, largely impermeable. Rain that falls on a road or a rooftop cannot soak into the ground beneath. It runs off immediately into gutters and drains and is carried away through underground pipes into rivers or treatment systems. The water is gone within minutes of falling. There is no reservoir of moisture sitting in the soil beneath the street, slowly evaporating through the day. The surface is dry, and dry surfaces have nothing to evaporate. trees in most cities are sparse and often stressed. The soil around them is compacted and covered, limiting their access to water. The buildings cast shade that complicates their growth, and so the vast, quiet engine of evapotranspiration that would be running continuously in a natural landscape is largely absent. The solar energy that arrives at a city's surfaces has nowhere to go but into warmth. Think about what this means in terms of energy. On a sunny summer day, a square meter of sunlit ground in a forest might receive around 600 watts of solar energy, roughly the power of a small household heater. In the forest, perhaps half of that energy goes into evapotranspiration, cooling the air and the ground. In a city, almost none of it does. The asphalt absorbs it, the concrete stores it, and it all becomes heat. The difference is not small. Studies comparing surface temperatures in urban parks with the surrounding city streets have found temperature differences of 2 to 5 degrees Celsius, sometimes more on hot days. The park is cooler not primarily because it is shaded, though shade helps, but because its grass and soil and trees are continuously spending solar energy on evaporation rather than on warming the ground. A single mature urban tree, one that has had the space and soil and water it needs to grow properly, can transpire between 200 and 400 liters of water on a warm day. That evaporation consumes a substantial amount of thermal energy, roughly the equivalent of running 5 or 6 household air conditioning units for several hours. The tree does not generate cold. It simply converts heat that would otherwise warm the air into the hidden form of energy carried away in water vapor. The effect on the air around it, in its immediate vicinity, within perhaps 20 meters, can be measurable. A degree or two of cooling maintained quietly through the heat of the day. Now imagine a street lined with trees, 20 of them, 30, mature and healthy, their canopies meeting overhead. The combined transpiration of that row would be removing enormous quantities of thermal energy from the street throughout the day, cooling the air, shading the pavement, slowing the absorption of solar energy into the road surface. The temperature difference between that street and an adjacent treeless one on a hot afternoon can reach 5 or 6 degrees. And then imagine the absence of those trees, which is the reality of most city streets in most cities in the world. The pavement bare, the sky open, the solar energy arriving and being absorbed without anything to spend it on except warmth. This is one of the quieter tragedies embedded in the urban heat island, not just that cities are warmer than they might be, but that the mechanism for cooling them, the living, breathing, water-cycling machinery of plants and soil, was largely removed in the process of building them and has never been fully restored. The cooling that a forest provides is not a luxury. It is a physical consequence of how energy works, and its absence in a city is written into the temperature of the air on every warm day and every warm night. The canyon and the wind, how street geometry traps heat and shapes air. A city is not flat. This seems obvious, but its implications for the way heat moves and accumulates are profound in ways that took researchers a long time to fully appreciate. Stand at the base of a tall building on a narrow street and look up. The sky is a strip, a rectangle of blue or grey between the roof lines on either side. The walls of the buildings rise on both sides of you, close enough that you could cross the street in a few seconds. This geometry has a name in urban climatology, an urban canyon, and it behaves in ways that are deeply different from open ground. To understand the first effect, what happens to sunlight in a canyon, you need to think about what a photon of solar radiation does when it strikes a surface that does not absorb it completely. Some of its energy is absorbed, yes, but some is reflected, bouncing back as light in a new direction. In an open field, reflected sunlight goes upward and outward, eventually escaping back to space. The surface reflects, and the energy is gone. In a canyon, reflected light does not necessarily escape. A photon that bounces off the east wall of a street might travel across and strike the west wall, where it is partially absorbed and partially reflected again. That second reflection might send it downward to the road surface, where it is absorbed again. Each time the photon strikes a surface, more of its energy is transferred into the material. The multiple reflections within the canyon effectively increase the total energy absorbed by the canyon's surfaces. The walls, the road, the narrower patches of sky between them. A canyon with tall, close walls can absorb significantly more solar energy than an equivalent area of flat, open ground, simply because the photons have fewer opportunities to escape. This effect depends on what researchers call the aspect ratio of the canyon, roughly the ratio of the building height to the street width. A narrow canyon with tall buildings on both sides has a high aspect ratio and traps a great deal of energy. A wide boulevard with low buildings has a low aspect ratio and loses energy more readily to the sky. This single geometric parameter, how tall the buildings are relative to how wide the street is, can dramatically affect how warm a neighborhood becomes. But sunlight is only part of the story. The other part is wind. Wind is one of the primary ways that cities lose heat. When air moves through a street, it carries warmth with it, sweeping the warm air that has accumulated near the ground away and replacing it with cooler air from elsewhere. This process, called advection, is the same one that makes a breeze feel cool on a warm day. Moving air is efficient at removing heat from surfaces and from the air layer just above them. In an open landscape, wind moves relatively freely, but in a city, tall buildings are obstacles and they alter the flow of air in complex and often counterintuitive ways. When wind encounters a tall building, much of it is deflected upward. It rises over the building rather than flowing through the street below. The result is that at street level, in the canyon between buildings, the air is often much calmer than you would expect given the wind speed measured above the rooftops. This sheltering effect was well understood in a general way for many years, but the details of how air actually moves inside a three-dimensional urban canyon, with real intersections, corner buildings, varying heights, turned out to be considerably more complex than the simplified models suggested. A study published in 2026 by Zhao and colleagues working with wind tunnel experiments and a technique called particle image velocimetry, a method that uses tiny particles suspended in the air and tracked by laser light to reveal the actual flow patterns, found that three-dimensional canyons behave in ways that simpler two-dimensional models had entirely missed. In a two-dimensional model, you imagine a canyon as a long, straight channel with uniform walls, and the airflow inside it is relatively orderly. But real canyons have corners, intersections, varying building heights, gaps and protrusions, and at these features the airflow becomes complex and layered. What Zhao and colleagues found were what they called corner eddies, rotating pockets of air that form where streets meet and where building heights change. These eddies are significant because they disrupt the simple pattern of air rising from the warm street surface and escaping upward. Instead, the eddies can trap warm air at street level, circulating it in place rather than allowing it to rise and be replaced by cooler air from above. The geometry of a single intersection, the precise arrangement of building heights and street widths at that particular corner, can determine whether warm air is efficiently vented upward or trapped and pooled. There is something almost uncanny about this. The temperature on a summer evening in a dense city district can vary by a degree or two from one block to the next, not because of differences in the materials or the vegetation or the traffic, but simply because of the geometry of the buildings, the particular angles and heights that determine whether a corner eddy forms and whether warm air is held in place. The lateral flows that Zhao's team also documented, air moving sideways along a canyon rather than simply up or down, add another layer of complexity. Heat generated or absorbed in one part of a canyon can be carried laterally to adjacent sections, spreading the warmth in ways that simple vertical models do not predict. This means that a single heavily trafficked intersection or a building with a particularly dark and heat-absorbing facade can influence the temperature of the surrounding streets in ways that extend well beyond its immediate vicinity. All of this geometry combines to create what, on a calm summer night in a dense urban district, becomes something almost tangible, the air barely moving, warmth pooling between buildings, the way water pools in a bowl, the street radiating heat from below and the walls radiating it from both sides, and no wind strong enough at street level to carry any of it away. The canyon traps the day, and the night inside it is warmer and stiller than the night outside the city, where the air moves freely and the heat disperses into the wide, patient dark. Heat, made by human hands, engines, air conditioners, and the city's own fire. There is a third source of warmth in a city beyond what the sun deposits and the ground retains. Cities generate heat from within, from the engines and furnaces and electrical systems and biological processes of their inhabitants. This is called anthropogenic heat, from the Greek for human-made, and in some cities, under some conditions, it is the dominant factor in the urban heat island. To understand anthropogenic heat, it helps to think carefully about where energy goes when it is used. Consider a car. It burns fuel, petrol or diesel, in its engine, and that combustion releases chemical energy that was stored in the fuel molecules. Some of that energy becomes mechanical energy. It moves the pistons, turns the wheels, propels the car forward. But a great deal of it, somewhere between 60 and 70%, depending on the engine, is converted directly into heat. It heats the engine block, which is cooled by water that carries the heat to the radiator, where it is released into the air. It heats the exhaust gases that flow out through the tailpipe. It heats the brakes when they slow the car. The car, in other words, is a machine for converting chemical energy into motion and heat, with a great deal more heat than motion produced in the process. And in a city, on a busy road, with thousands of cars moving through the streets, all of that waste heat is released directly into the urban air. Industrial processes do the same thing on a larger scale. Manufacturing, food processing, power generation, all of these convert energy into useful work and heat, and the heat goes into the air and the ground and the water around them. But perhaps the most interesting and counterintuitive source of anthropogenic heat in a modern city is the air conditioning system. An air conditioner does not destroy heat, it moves it. The device works by circulating a refrigerant, a fluid that evaporates and condenses readily between two sets of coils. In the indoor coils, the refrigerant evaporates, absorbing heat from the room air and cooling it. In the outdoor coils, the refrigerant condenses, releasing that heat into the outside air. The room is cooled. The outside is warmed. Think about what this means at the scale of a city. On a hot summer day, every air conditioner in every office building, apartment and shop is drawing heat from its interior and pumping it outward into the street. The streets are already warm from solar absorption and reduced evapotranspiration, and now they are receiving additional heat from thousands of outdoor condenser units, their fans blowing warm air into the already warm urban atmosphere. Walk past the base of a large office building on a summer afternoon, and you can feel it, the warm exhaust from the building's cooling system washing over you, noticeably warmer than the ambient air. And here is where the feedback loop becomes particularly striking. The city is warm, so people run their air conditioners. The air conditioners pump heat into the city, making it warmer. The warmer city causes people to run their air conditioners more intensively, which releases more heat, which makes the city warmer still. This is a self-reinforcing cycle, and it tightens with every degree of background warming. As the global climate warms, cities that were already hot become hotter. the demand for air conditioning increases, the heat pumped into the streets increases, the urban heat island intensifies, and the increased electricity consumption needed to run all that cooling, much of which is still generated from fossil fuels, adds its own contribution to the warming of the broader climate. Research on cities in colder climates has found that the balance of anthropogenic heat sources shifts dramatically with the seasons. In a city like Tomsk in western Siberia, the urban heat island in winter is driven not primarily by solar absorption or reduced evapotranspiration. In a frozen, snow-covered landscape, those factors are relatively minor, but by the direct output of heat from buildings, industrial processes, and vehicles. Estimates suggest that in Tomsk's winter, anthropogenic sources account for between 80 and 90% of the heat island effect. The city is warmer than its surroundings almost entirely because of the heat that human activity generates directly. In summer, the balance shifts, solar absorption and the absence of evapotranspiration become more important, and anthropogenic heat accounts for perhaps 40 to 50% of the effect. But it is never negligible. Even in the warmest months, the heat that human hands generate, from engines, from factories, from the outdoor units of air conditioners, is a substantial contributor to the urban warmth. There is something worth sitting with in this. Luke Howard, walking between Tottenham and the city in 1820, speculated that fuel burning was one of the causes of London's excess warmth. He was right. But the scale of fuel burning in a modern city and the complexity of the pathways through which that energy becomes heat in the urban air would have been beyond his ability to imagine. Every car engine, every air conditioning unit, every industrial process is a small fire, releasing energy that was stored in fuel or generated from electricity, and that energy, all of it, eventually, becomes warmth in the city's air. The city burns, quietly, continuously, from 1,000 sources too small to notice individually, but collectively enormous. And all that burning adds its warmth to the warmth of the sun and the warmth of the stone, layer upon layer, through the day and through the night. Rain, ozone, and the weather a city writes for itself. The urban heat island does not merely raise the temperature of a city. It reaches outward from that single effect and rewrites, in subtle and significant ways, the entire character of the local weather. A city, it turns out, is not simply a place where the regional climate arrives and is modified by buildings and roads. It is a place that actively participates in creating its own atmospheric conditions, a conversation between stone and sky that continues without pause. To understand how, start with the simplest consequence of a city's warmth: warm air rises. This is basic physics. Warm air is less dense than cool air. When a parcel of air near the ground is warmer than the air above it, it tends to rise, carrying its moisture and warmth upward. In a natural landscape, this process, called convection, happens gently and relatively slowly, driven by the uneven warming of the ground by sunlight. But above a city, where the surface is consistently warmer than the surrounding countryside, the rising is more vigorous and more persistent. There is a column of warm, rising air above a city, and it has consequences. One of them is rainfall. As air rises, it cools, and cool air holds less water vapor than warm air. When rising air cools enough, the water vapor in it begins to condense into tiny droplets, forming clouds. If the process continues, those droplets grow and eventually fall as rain. Cities, because of their persistent warm updrafts, can trigger their own convective rainfall. The warm air rising from the city pulls moisture-laden air in from the surrounding countryside, carries it upward, and produces clouds and sometimes storms, often not directly over the city itself, but downwind of it, where the rising air encounters cooler air aloft and the conditions for rainfall are met. This effect has been documented in cities around the world. Studies have found that rainfall downwind of major urban areas can be measurably higher than the regional average, particularly in summer when convection is strongest. The city, in effect, seeds the atmosphere around it with its own warmth, and the atmosphere responds by producing weather that would not otherwise have occurred. But rainfall is only one thread in a more complex story. The other thread is chemistry, and here the urban heat island interacts with something that is itself a product of city life: air pollution. The air above a city contains a mixture of gases that would not be present in significant quantities over open countryside. Among the most important are nitrogen oxides, molecules produced whenever fuel is burned at high temperatures, as in a car engine or a power plant, and volatile organic compounds, a broad category of carbon-containing gases that evaporate from fuels, solvents, paints, cleaning products, and countless other urban sources. On their own, these molecules are unpleasant but relatively manageable, but in the presence of sunlight, they react with each other to produce ground-level ozone. Ozone, a molecule made of 3 oxygen atoms bound together, is familiar as the protective layer high in the stratosphere that shields the Earth from ultraviolet radiation. But at ground level, it is something quite different: a reactive, irritating gas that damages lung tissue, worsens asthma and other respiratory conditions, and, at sufficient concentrations, poses a genuine health risk. The critical point, for our purposes, is that the chemical reactions that produce ground-level ozone are strongly accelerated by heat. Higher temperatures mean faster reactions, which means more ozone produced from the same quantity of precursor gases. A city that is 3 degrees warmer than its surroundings will produce significantly more ground-level ozone than it would if it were cooler, even with exactly the same traffic and the same industrial activity. A study published in 2025, which analyzed data from 776 air quality monitoring stations across the United States, found that 9 in 10 of them showed a significant positive relationship between temperature and ozone concentration. Not a correlation that might be explained by seasonal patterns or confounding factors, but a direct, robust link: higher temperatures, more ozone. And since urban heat islands make cities consistently warmer, they are also, through this chemical pathway, making city air consistently more polluted with ozone than it would otherwise be. And ozone, in turn, has its own effect on temperature. At ground level, ozone absorbs infrared radiation, the same kind of heat radiation that the warm ground emits upward through the night. When ozone absorbs that radiation, it re-emits some of it back downward, adding a small but real contribution to the warming of the air near the surface. The city's warmth produces ozone, and the ozone helps the city stay warm. Another loop, another self-reinforcing cycle, woven into the fabric of the urban atmosphere. There is something almost organic about the way all these cycles interact. The city generates heat. The heat drives convection. The convection pulls in moisture and can produce rainfall. The heat also accelerates chemistry, producing ozone. The ozone traps more heat. The warmth drives more air conditioning, which produces more heat. Each effect feeds the others, and the whole system, city and atmosphere, stone and sky, is in a continuous, dynamic conversation that reshapes the local weather around the clock. A city's climate, in this sense, is not simply the regional climate experienced through the filter of streets and buildings. It is something the city makes, actively and continuously, from the raw materials of sunlight and pollution and warmth and rising air. The weather above a city is, in part, the city's own creation. And that creation does not fall equally on everyone who lives within it. An unequal heat: who bears the warmth and who does not? The urban heat island is not a single, uniform warmth spread evenly across a city. If you could look at a city from above with instruments sensitive to temperature, as satellites now routinely do, you would see not one island but an archipelago, a landscape of varying warmth, with some neighborhoods glowing several degrees hotter than others, and the pattern of that variation following lines that have nothing to do with geography and everything to do with history. The hottest parts of a city are almost never the wealthiest parts. They are, with a consistency that holds across city after city and country after country, the parts that have been most disinvested, the neighborhoods that receive the least maintenance, the fewest trees, the oldest and least efficient housing, the most industry and the most traffic. And those neighborhoods, in city after city, are disproportionately home to people of color and people with lower incomes. This is not coincidence. It is the accumulated physical consequence of decades of policy decisions. In the United States, the clearest historical mechanism is what is known as redlining, a practice that was formally implemented in the 1930s when federal agencies created maps of cities and color-coded neighborhoods by their perceived investment risk. Neighborhoods where black residents lived were systematically marked in red, indicating that they were high risk for mortgage lending. Banks refused loans in these areas. Businesses declined to invest. The housing stock deteriorated. Public services, including tree planting and park maintenance, were reduced or absent. The physical consequences of that disinvestment are still visible in the landscape today, and they are measurable in temperature. Neighborhoods that were redlined in the 1930s tend, decades later, to have fewer trees, more impermeable surfaces, older buildings with poor insulation, and more heat-generating land, uses like industrial facilities and busy roads. The result is that the communities that were historically denied investment are today bearing a disproportionate share of the urban heat island's burden. The numbers are striking. Research analyzing surface temperature data across major American cities found that black residents are around 50% more likely than white residents to live in the hottest parts of urban heat islands. A systematic review published in January 2026 found that disadvantaged urban communities face between 3 and 4 degrees Celsius, more heat exposure than wealthier neighborhoods in the same city, and between 26 and 45% higher rates of heat. 3 to 4 degrees. That is not a small difference. It is the difference between a warm night and a dangerous one. It is the difference between discomfort and a medical emergency for someone elderly or ill or working outdoors. And it falls, with remarkable consistency, on the people least able to escape it. Those who cannot afford air conditioning, or who live in older buildings that trap heat, or who work in outdoor or physically demanding jobs that leave them already depleted when the evening warmth arrives. The mechanisms behind this disparity are several, and they compound each other. Fewer trees means less shade and less evapotranspiration, both of which, as we have already traced, are primary cooling mechanisms. More asphalt and concrete means more solar absorption and more stored heat released through the night. Older housing stock with poor insulation means indoor temperatures that track outdoor temperatures more closely, with less ability to maintain a cooler interior during a heat event. More traffic means more anthropogenic heat and more air pollution, including the ozone whose production is accelerated by warmth. Each of these factors is, individually, a meaningful contribution to local warming. Together, they create neighborhoods that can be 5 or 6 degrees warmer than the leafy, well-maintained districts a few kilometers away. Districts where the trees are large and plentiful, the roofs are light-colored or well-insulated, the roads are less heavily trafficked, and the residents have the resources to air-condition their homes and take breaks from the heat. This is where the science of urban climatology meets something that is not merely scientific. The urban heat island is a physical phenomenon, yes. It follows from albedo and evapotranspiration and thermal mass and airflow, all the things we have traced through the earlier chapters. But the pattern of who experiences its worst effects is a human construction, built over decades through choices about where to invest and where to withhold, where to plant trees and where to pave, whose comfort mattered and whose did not. The solutions being tested in cities around the world are, in this light, not just engineering projects. They are also acts of remediation. Urban greening programs, systematic planting of trees in historically underserved neighborhoods, are among the most studied interventions. The cooling effect of a single well-placed street tree, shading the pavement and transpiring water through the warmth of the day, extends perhaps 20 meters in each direction. A row of mature trees can reduce street-level temperatures by several degrees. And the trees accumulate. As they grow, their canopy expands, their root systems deepen, their transpiration increases. A tree planted today will still be cooling the street 30, 50, 100 years from now. Cool pavement programs replace dark asphalt with lighter-colored materials or reflective coatings, raising the surface's albedo and reducing the heat it absorbs. Pilots in cities including Los Angeles have found surface temperature reductions of several degrees, measurable on the street itself and, to a lesser extent, in the air above it. Green roofs, rooftops covered with soil and plants, add transpiring surfaces to what would otherwise be vast expanses of heat-absorbing material. They insulate the buildings beneath them, reducing the need for air conditioning and therefore the anthropogenic heat pumped into the street below. They also manage rainfall, holding water that would otherwise run off immediately into drains and releasing it slowly through evaporation over the following days. None of these solutions is simple to implement at scale. Trees take decades to grow. Cool pavements require maintenance and eventual replacement. Green roofs are expensive to install, and the communities that most need these interventions are often the least equipped, financially and politically, to advocate for them. But the physics is clear. The cooling that these measures provide is real and measurable. A street with trees and lighter surfaces and green roofs is cooler than a street without them. Not marginally cooler, but meaningfully, significantly cooler, in ways that affect health and comfort and sleep and the quality of life of the people who live there. The heat is unequal. The solutions are known. The distance between those two facts is where the work remains to be done. The warm night and the body that cannot cool. Somewhere in a city tonight, a person is lying in bed, unable to sleep. The room is warm, the window is open, but the air coming through it is not much cooler than the air inside. The street below is still radiating heat from the stone and asphalt that absorbed the day's sunlight, releasing it slowly back into the night. The person turns over, pushes the covers aside, lies still. The warmth does not relent. This is not merely uncomfortable. Something specific is happening inside that body. A biological process that requires coolness to complete itself, and that is being gently, persistently frustrated by the warmth the city is holding. To fall asleep, the body must cool itself. This is not a metaphor or a general observation. It is a precise physiological requirement, as fundamental to the process of falling asleep as darkness is to the process of melatonin release. The brain's internal clock, which sits in a small cluster of cells deep in the hypothalamus, begins preparing the body for sleep in the late afternoon and early evening. One of its primary tools is temperature regulation. About 2 hours before a person's typical sleep time, blood vessels in the hands and feet begin to dilate, to widen. More blood flows to the skin's surface. More heat radiates outward from the extremities into the surrounding air. The body's core temperature, the temperature of the deep internal organs, the brain, the heart. This drop is not incidental. It is the mechanism. The falling core temperature is itself a signal to the brain that sleep is near, and it is one of the primary triggers for the onset of drowsiness and the transition into sleep. For this to work, the surrounding air needs to be cool enough to accept the heat the body is trying to shed. The body is trying to offload warmth through the skin of the hands and feet, through the breath, through the gentle radiation of heat from the body's surface. If the air around it is already warm, that process is slower and less efficient. The core temperature drops more slowly. The signal to the brain is weaker. Sleep is harder to reach. Research consistently places the optimal sleeping temperature for most adults somewhere between 15 and 19 degrees Celsius, roughly 60 to 67 degrees Fahrenheit. Within that range, the body can cool efficiently. The transition into sleep is smooth, and the architecture of sleep through the night is preserved. Below that range, the body must work to generate heat, which is its own kind of disruption. Above it, now consider what the urban heat island does to that range on a warm night. The stone and concrete outside have been absorbing solar energy since morning. By the time the sun sets, they are full of stored warmth, and they spend the night releasing it, slowly, continuously, warming the air that sits between the buildings and the air that drifts through open windows into bedrooms. In a city neighborhood with dense buildings and little vegetation, the air temperature at midnight on a warm summer night might be 3, 4, or 5 degrees warmer than in the countryside a few kilometers away. In the most heat-affected urban neighborhoods, those with the fewest trees, the most asphalt, the oldest housing, it can be warmer still. A bedroom in such a neighborhood on a warm night might sit at 22 or 23 degrees even with the windows open. The body lying in that room is trying to shed heat into air that is already warm. The cooling that needs to happen, the gentle, gradual drop in core temperature that the brain is waiting for, is slow and incomplete. And this is where the consequences reach into the deep structure of sleep itself. Sleep is not a single state. It is a sequence of stages, cycling through the night in a pattern that is both ancient and intricate. The earliest and deepest stages, what researchers call slow-wave sleep or deep non-REM sleep, are characterized by slow, large electrical waves rolling through the brain, a kind of deep quiet in which the body does its most intensive repair work. Tissue is rebuilt. The immune system is reinforced. The events and information of the day are transferred from temporary storage in the hippocampus to longer-term networks across the brain. This stage is the most physically restorative part of sleep, and it is concentrated in the first half of the night. Then, cycling upward through lighter stages and back, comes REM sleep, rapid eye movement sleep, the stage in which dreaming is most vivid and most structured. REM sleep has its own restorative function, distinct from slow-wave sleep. It is the stage in which the brain processes emotional experience, integrates new learning with existing memory, and does a kind of nightly maintenance on the emotional and social circuits that govern how we feel and how we relate to others. Both stages are disrupted by heat, but they are disrupted in different ways and for different reasons. Slow-wave sleep is reduced when the body is thermally stressed. The brain, unable to complete the cooling it requires, cycles through the deep stages more briefly, surfaces into lighter sleep more frequently, and accumulates less of the slow-wave activity that the night should contain. The person wakes more often, sometimes briefly enough that they do not remember it in the morning, but enough that the continuity of deep sleep is broken. By morning, they have had less slow-wave sleep than they needed, and the physical restoration that should have occurred is incomplete. REM sleep is vulnerable to heat for a more fundamental reason. During REM sleep, the body largely suspends its own temperature regulation. The mechanisms that normally keep the body's temperature stable, shivering when cold, sweating when warm, are largely inactive during REM. The body becomes, for the duration of that stage, almost ectothermic. Its temperature tracks the environment rather than regulating itself. This makes REM sleep uniquely sensitive to ambient temperature. If the room is warm, the body warms during REM, and the stage is cut short. The brain surfaces into lighter sleep or into waking, and the emotional processing and memory integration that REM provides are truncated. Night after night, in a warm urban bedroom, this adds up. Less slow-wave sleep means less physical restoration, less immune reinforcement, slower recovery from the accumulated wear of daily life. Less REM sleep means emotional experience that is less fully processed, memory that is less well consolidated, a subtle but real erosion of the brain's ability to manage stress and regulate mood. The warmth outside is not just uncomfortable, it is reaching into the sleeping brain and reshaping what the night provides. And the effects are not evenly distributed. As we traced in the previous chapter, the warmest urban nights fall most heavily on the communities with the least access to air conditioning, the oldest housing, the fewest trees outside their windows. The heat that history has concentrated in certain neighborhoods reaches into the bedrooms of those neighborhoods and takes something from the people sleeping there night after night in ways that are real and measurable, but largely invisible. Widen the view now, slowly. 3 in the morning in a dense city neighborhood. The streets are quiet, the windows are open, the stone walls of the buildings are still warm to the touch, still releasing the day's sunlight in long, slow waves of infrared radiation. The air between the buildings is still, held by the geometry of the canyon, barely moving. A few degrees warmer than the fields beyond the city's edge, a few degrees warmer than it needs to be. Inside the buildings, people are restless, turning over, surfacing briefly into partial waking, drifting back down. The city they live in was built without much thought for this, for the temperature of a bedroom at 3 in the morning, for the body's slow, necessary cooling, for the quality of the sleep that the night should provide. It was built with other priorities: efficiency, density, the movement of goods and people, the accommodation of commerce and industry. The warmth was a byproduct, unnoticed for a long time, named only in 1929, understood only gradually through the decades that followed. But it is understood now. The mechanisms are clear. The albedo of dark surfaces and the thermal mass of concrete and the absence of trees and the heat from engines and air conditioners and the geometry of canyons that trap warm air, all of it is traceable, measurable, and to a meaningful degree reversible. Lighter surfaces reflect more sunlight. Trees transpire water and shade the pavement and cool the air beneath them by several degrees. Green roofs add transpiring surfaces to what would otherwise be heat-absorbing expanses. Streets designed with ventilation in mind, wider with gaps between buildings that allow air to move, shed their warmth more readily as the night deepens. None of it is impossible. Some of it is already happening in cities that have begun to take the warmth seriously. Planting trees in the hottest neighborhoods, piloting cool pavements, retrofitting rooftops, rethinking the geometry of new streets. The changes are slow, as changes in cities always are. Trees take decades. Trees take decades. But the physics does not change. Every tree planted is cooling the air beneath it today and will cool it more as it grows. Every light-colored roof is reflecting sunlight that would otherwise become heat in the stone below. The city at 3 in the morning, the warm streets, the restless sleepers. It does not have to be quite this warm. Somewhere behind the buildings, the countryside is already cool. The fields have given up their heat hours ago. The air above them is still and quiet and several degrees gentler. The difference between that air and the air in the warm canyon of the city street is the accumulated result of everything we have traced tonight. The albedo of asphalt, the absence of trees, the heat from 10,000 engines, the geometry of walls that trap what the ground releases, the history of decisions about where to invest and where to let things run down. All of it, in the end, comes back to warmth, and to the body lying in it, trying to cool. Let the city settle now, if you can. Let the warmth be something distant, something you understand, something that can be changed, something that patient work and lighter surfaces and more trees and better choices are already, slowly, beginning to address. The night is long. The stone outside is still warm, but it is cooling, degree by degree, as the hours pass. Let your own warmth settle. Let your hands and feet do what they are trying to do. Release the day's heat gently into the air. Lower your core temperature by the fraction of a degree that the brain is waiting for. The city is quieter now. The streets are still. Somewhere, a tree is transpiring its last few molecules of water into the dark air, cooling the pavement beneath it by something too small to measure, but real nonetheless. And so we leave it there. Somewhere behind you, the day is already distant. Let it stay there. Drift now, if you are ready. Sleep well.